Good afternoon. From the title, we can see that the work reported here covers a wide range of topics, so that in this presentation, obviously, I can only make brief reference to each aspect. The whole project was made possible by the installation of a 2K by 2K camera at the EDF laboratories in France, and we're indebted to Dominique Lasnoire, who recorded all the patterns that we have used in this presentation. We'd also like to acknowledge Austin Day, who has provided the computer simulations for the patterns used throughout. We studied 4 materials: strain-free germanium, body center cubic iron, which was part of a duplex steel structure, the other phase being face center cubic iron, and PZT, a tetragonal structure which was in a state of high strain. The aim was to develop a method of obtaining accurate angular measurements of relating crystallographic features in the patterns to enable the crystal symmetry, unit cell construction, and absolute strain measurements to be made. The path we took was 1. To accurately determine the Kikuchi band positions in the EBSD image. Then to determine the pattern center and the Z-star values at high accuracy. Thirdly, to develop a shadow casting procedure for universal pattern center and Z-star value measurements. Fourthly, to determine orientations accurately. And fifthly, for absolute strain measurement. The first point is to determine accurate locations of the Kikuchi bands. We've abandoned the Huff trace procedure that is normally used, replacing it with a tangent tracing procedure and a hyperbolic tracing procedure. In the tangent tracing procedure, the pixel intensities are summed along all possible straight lines that we can draw in the pattern. The output we choose to use is a gradient map. Example outputs are shown below for inclined bands and for horizontal bands. The changing gradients at the band edges are very sharply defined, and the red lines are shown below are the join the points of maximum gradients. The asymmetry in the figure for the inclined bands is an important feature, and accurate determination of the band center can only be made if this is taken properly into account. This is exactly what is missing in the normally used Huff transform. The subsequent hyperbolic trace is made using the θ5 values at the midpoints of the red lines. Hyperbolic tracing removes the asymmetry so that the 2 points of maximum gradient lie at the same θ value. The experimentally found band edges using hyperbolic traces are shown in the EBSD map below in green. The band center lines are in blue. The accuracy is assessed from the scatter of the blue center lines from the mean point. The scatter can be quantified, and the table shows the results that we've obtained for the 4 materials, both for when we use the hyperbolic refinement and when we switch it off. We can see using the best case, the germanium with the hyperbolic refinement on, that the average scatter for 42 zone axes was just over 1/100 of a degree. If we proceed to the PZT, our worst case, but also with the hyperbolic refinement on, it's reduced to 1/10 of a degree. Having secured a means of accurately determining the Kikuchi band positions, we turn to a method for determining the pattern center and specimen to screen distance accurately as well. We've adopted the standard technique now of comparing the experimental pattern with a computer simulation of that pattern, and we have done this for the 4 materials studied. We've adopted the WMD method for cross-correlating images, where the cross-correlation is for a network of identical regions of interest arranged in the 2 images. The cross-correlation outputs the displacements between the experimental image and the simulated image in each ROI. And the displacements vary from ROI to ROI in a systematic way. And it is dependent on the type of the misalignment, either whether it is due to a rotation or to an error in the PCXY position or the specimen to screen distance. The next few slides illustrates the convergence from the original misalignment for each ROI to the point of near perfect alignment. The blue dots show the centers of the regions of interest, and the red dots the initial displacements for each ROI. The magnitude of the displacement is magnified for convenience by a factor of 10. The systematic nature of the misalignments throughout the regions of interest is quite clear to see, and it is obvious that there must be a misalignment of the two images by a rotation about the z-axis. In this slide, we've applied a 0.14 degree rotational correction around the z-axis. We see that the correction has aligned the displacements to be almost parallel to the ROI centers. However, because there is a displacement to the right of the red dots, then it means that the PCX value must be too far to the right. However, as there is also a difference in magnitude of the displacement between the left and right of the diagram, it means there must also be a rotational element to the observed displacements. In this slide, we show the effects of a correction in PCX by 0.2 pixels and a rotation about the y-axis of minus 0.21 degrees. We can see an improvement in the alignment, but it is still poor at the bottom of the image, indicating a correction about the x-axis similar to the one we've just done about the y-axis. In this slide, we show the effects of having a correction about the x-axis of 0.72 degrees rotation and a shift in the PCY position of 14.8 pixels. At first sight, the alignment seems to be worse, but careful inspection shows that in fact all the displacements are aligned along radii going through the pattern center, and this is indicative of a zoom effect. And the right-hand figure shows the zoom effect corrected by a change in Z star of 12.2 pixels. We now have almost perfect alignment between the two. Having convinced ourselves that we can get near perfect alignment, the technique has been automated using a downhill simplex minimization routine, and the figures here show the difference in results between the manual method and the automated method, and it's just a few hundredths parts in a pixel. Over here we see the final residual errors in both X and Y, and if we want to convert those errors into microns in the image, it turns out to be an uncertainty of 1.8 microns on average in PCX, PCY and Z star. We applied this technique to the other materials we were studying, but got disappointing results. But as we can see, only parts of the pattern proved to produce a high degree of convergence, whereas other parts of the pattern were very poor. We therefore decided to adopt a different method of determining the pattern center in these other materials. We have been using for some time a shadow casting technique to overcome the problems I've just discussed, and in fact I did report it in 2014. It consists of a circular aperture which casts a shadow onto the screen, and from the measurement of the center of the shadow and the radius of the shadow, we can back calculate the positions of the beam on the specimen and hence the pattern center position on the screen. It needs calibrating, however, and we've used the cross-correlation procedure I've just described, using a germanium crystal as the specimen to do the calibration. We need to calibrate 4 parameters of the shadow casting apparatus, and here are the results for 5 it's different orientated germanium specimens, and these are the standard deviations over those 5 of these parameters, and we see that they're all better than the half a pixel. If we put these errors together, that is the error in determining the shadow perimeter and the error in the calibration, then the resulting accuracy of finding the PC and Z star values is 3 parts in 10,000 of the screen diameter. We turn now to the determination of orientation. At the beginning, we start the same way as standard methods, that is to say, we convert the bands detected into the directions of the plane normals. And then we take pairs of bands, look at the interplanar angle, and then deduce what the Miller indices of each band must be. For each index pair, however, we then calculate an orientation. And the pair that provides the over-orientation with the best fit with the experimental pattern is chosen as the one that is the most likely true orientation. Best fit is measured from the number of experimentally determined band normals that fall within 0.2 degrees of their theoretical position, together with the average misalignment of these plane normals. For example, for the 30 bands selected in germanium, there are 870 orientations to be tested. For our observed best fit case, 28 of the 30 plane normals were oriented within 0.2 degrees of the theoretical position, with an average absolute error of 0.5 degrees, or 0.0008 radians. In comparison, for the output orientation for the PZT patterns, typically only 7 plane normals were oriented within the 0.2 degrees tolerance angle, with an absolute average error of 0.1 degrees. Although this is only 2 times poorer than the germanium, only 7 bands set the tolerance as opposed to the 28 for germanium. It does suggest, however, that we still have determined the orientation with very high accuracy, but that many of the bands are poorly defined, and that we need to indicate the reasons why so many are poorly defined. We can test how accurately we have determined the orientation by measuring the interplanar angles and look at the errors involved. For a perfect crystal, we expect the errors in the interplanar angles as measured to have a Gaussian distribution, and that's exactly what we see for the case of germanium below. The deviation of the peak of the Gaussian from 0 gives us an indication of the error we might be expecting in the orientation measurement, and as seen, it is 5 parts in 10,000. If we look at the results for the face center cubic iron, we see that the Gaussian is not so good, although the fractional error of displacement of the peak is now only 7 parts in 10,000. A very little difference, but the uncertainties in the Gaussian suggest a poorer result. We can carry out a similar analysis on the interzone axis angle errors. The results for the germanium sample are very similar to those that we obtained with the interband angle measurements. The results for the iron are slightly worse. It shows here that the normalized errors in the iron are 15 parts in 10,000, whereas in the germanium case it was only 2 parts in 10,000. This needs investigating. We can obviously look directly at the orientation measurements, and the results you're seeing are for 9 points on a scan for the single crystal germanium, and we can see from the average values that the error is something like 0.01 degrees, that is 2 parts in 10,000. We can obtain a visual impression of the quality of the orientation measurement procedure from the computed overlay, and the left diagram shows the results for the overall pattern, and the right diagram shows the results for a detail. The green lines are hyperbolic traces obtained experimentally, and the white lines are the computed overlay, and as you can see, it's almost impossible, in fact impossible, to tell the difference between the experimental and the computed overlay. We turn now to absolute strain measurement, and in this case the reference pattern is a computed simulation taken in the zero strain condition. In our case, the pattern center for the simulation is that obtained from the shadow casting technique, and the orientation obtained using the method I've just described above. The results shown are for 5 scans on the surface of single crystal germanium. The upper data is for the first line of one of the scans, and the second set of data is for the average of all 5 scans. Both show that the errors look like less than 4 parts in 10,000, both in the strain components and in the rotational components. To finish, I'd just like to point out the developments on the speed of the processing. When we started, it took 15 seconds for the tangent tracing procedure and 40 seconds for a hyperbolic refinement. With the application of a GPU system, tangent tracing now takes 32 milliseconds and the hyperbolic refinement to 83 milliseconds. If we'd had the GPU at the start of the project, then it would have been done in half the time that it's actually taken. Thank you very much.